All right, we are going to hopefully finish out chapter 2 here of Campbell's biology, finishing up our basis for the chemical context of life. All the future chapters are going to really build onto this, okay? So it's important to have the foundations down in order to be able to pile the new stuff on in the future. All right, so I'm introducing a new concept that isn't in the book. I'm going to call it concept 2.3 and 2/3. This is part of concept 2.3. It's discussed there, but they don't really draw as much attention as I wish they did. So here, the molecular shape is crucial in biology because it determines how biological molecules specifically recognize and respond to one another. Okay? I want you to understand that there is a relationship between shape and function. Okay? A molecule's shape is usually very important to what it does. And this isn't just true for molecules, this is really true of everything. Okay? Think about these two objects here. So here we have a glass. Okay, it's kind of a cylinder. It has glass walls. Over here we have a glass tube. Okay, this functions as a cup. Despite how similar this tube is to that cup, this tube can never function as a cup. There is no bottom to hold the water. Okay, that seems like maybe silly and stupid and obvious, but I want you to recognize that that same stupid obviousness is true at the molecular level too. Things are shaped a particular way to do a particular function. So these two are not equal. And another way of expressing this idea up here is structure is function. Okay? Structure determines function. It's all related. Now, a molecule's shape is determined by the position of its atoms' orbitals. Okay, and you guys remember orbitals, right? Here's the first shell s orbital, here's the first shell, or the second shell s orbital, and then we have the 3 second shell p orbitals. Okay? Now, when you introduce covalent bonds, the s and p orbitals may hybridize and creating a specific molecular shape. This means that when the atom is existing by itself, its electrons are going to be in these orbitals the way we described them. But when you introduce a covalent bond, that changes everything. Okay, and we'll explain why here in a moment. Okay. So just to remind you, we have this outer valence shell. It has these pairs of electrons in the 2s orbital, in the 2px, the 2py, the 2pz. And these outer valence electrons are what's interacting with the world around it. Okay, it's what touches everything around it. I also want you to remember that these nucleus is positively charged and the electrons are negatively charged. Okay. Now, when we start thinking about forming covalent bonds, what I want you to recognize is that these two electrons are being shared by both of these nuclei. That's going to change its distribution. Okay, and the same is true for all of these. So let's take a look, and I'm just going to pick a p orbital here for ease of explanation. Okay, so here we have a simplified view. We have two atoms that are come together to form a molecule, and they're going to share electrons. Here I'm only showing one p orbital because it just so happens that this is the p orbital where the single electrons are that are going to be shared. Okay, so the first step is these things become close together and we have an electron present in this system. Okay, now remember that in the original orbital that these electrons were kind of rotating in these two lobes because they were being attracted solely to the nucleus. In this new scenario, we have electrons being attracted to both of these nucleuses. So it stands to reason that the electrons would be present in the space in between more often than they'd be present over here or over here. Okay? So, in reality, that is going to look something more like this. So the electrons are mostly here. Every once in a while you might see it over here, or you might see it over here. Now, let's think about this. If we've changed the actual shape of the orbitals, it is no longer a p orbital. We can't describe it that way. It is something else. We'll call that something else a hybrid orbital. Okay? Now, also keep in mind that we have other orbitals present too. So let's just put one in. Okay, here's another p orbital. Notice that this lobe is smaller than this big lobe over here, and bigger than this tiny lobe over here. These lobes have electrons in it, so the electrons may be over here, over here. Most of the time, these electrons are going to be right here. They are negatively charged. They are going to repel each other. The same is true over here. That is going to cause these lobes to change and push away. Okay? And it does it in a kind of surprising way. So when you have an s orbital and three p orbitals, it turns into 3 or 4 new completely different orbitals that form this shape here. So here we have one big lobe that replaces one orbital. And what they don't show you here is there is actually a little tiny lobe that should extend on the other side of the nucleus, but it's tiny in comparison to this side. And here we have another lobe, and here we have another lobe, and here we have another lobe. So we have 1, 2, 3, 4 orbitals. And if you recall, we're starting off with 4 orbitals, an s orbital and 3 p orbitals. So the s and 3 p orbitals become these 4 new hybrid orbitals that we will refer to as sp3 orbitals. And there are, in fact, 4 of them. They kind of form along an axis, or kind of a trigonal pyramid shape that we call tetrahedron. Okay, so if you can imagine this being a pyramid sitting in the background, and the base of this pyramid has 3 corners, and each lobe is focused towards a different corner, and in the center of that pyramid is where the nucleus would sit. Okay, this tetrahedral shape is what a lot of molecules form into. Okay? In both the case of methane and water, this is what happens. Okay? So here we are going to look at what's happening with the orbitals of the carbon, but something similar is kind of happening with the hydrogen as well. So here's the carbon, and we originally had those s and 3p orbitals. Now they squeeze into this new position, okay? And it's squeezed into this new position so that each one of these hydrogens are as far away from each other as possible. And here's looking at a 3D model of how that would actually look. So you have kind of a ball in the middle, and these half globes kind of sticking off in the furthest possible directions from each other. That happens to be 109 degrees. So there's 109 degrees between here and here, between here and here, between here and here, between here and here. I think that's all of them. No, actually between here and here, and between here and here, all 109 degrees. Okay. Water will take a similar shape, and instead of having something bonded to these other orbitals, we will have an unbonded electron pair sitting in that orbital. Now, something that I want you to keep in mind is these orbitals over here have lone electron pairs, so they are all negative. and they are pushing against one another. These hydrogens are going to be positively charged, but they also have electron orbiting as well. Granted, that is most of the time pulled towards the oxygen, so you get a partial charge, but it does dampen the effect. So water, something a little funny happens, in that these two hydrogens can get squeezed a little bit closer together because these negative charges on these on-bound electron pairs are kind of pushing at it. And the repulsion between the hydrogens is slightly less because they are, in fact, sharing electrons. So there is both positive and negative. Now, the reason why I'm spending so much time on this is the molecular shape is crucial in biology because it determines how biological molecules specifically recognize and respond to each other. Okay? Opiates, such as morphine, and among others, and naturally produced endorphins have similar effects in the body because their shapes are similar and they bind the same receptor in the brain. Okay? So here's kind of a picture representing that. This is actually what natural endorphin looks like. Okay? This is actually what morphine looks like. Down here, we have a representation that this endorphin receptor that's in your brain cells is binding this region right here. If you look at this region, that looks extraordinarily similar to this region on morphine. Okay? The fact that they look the same means that they can both bind to these sites. So it's simply a coincidence that we were able to find a natural compound coming out of a plant that happens to look like this molecule over here and happens to trigger and activate these receptors. This is pretty much what happens for most drugs. It is binding something in the body that something else should be binding to, and it's either activating something or inhibiting something or having some other type of regulatory effect. Okay? So, concept 2.3 2/3, molecular shape is critical in biology because it determines how biological molecules specifically recognize and respond to one another. Okay, so we have these 4 orbitals, an s and 3 p's, becoming 4 sp3 orbitals, which have this tetrahedron shape. Now, briefly, we're going to go into concept 2.4, which is chemical reactions make and break chemical bonds. That is what we mean by chemical reactions. It's just all about the formation of these chemical bonds. Okay? Now, when you are starting, when you look at the starting molecules of a reaction, we will call those reactants. The final products of the reaction we call products. Okay? So here we have hydrogen reacting with oxygen, forming water. These are the reactants. These are the products. Okay. Another thing, photosynthesis is very important to us. Light powers this conversion of carbon dioxide and water into glucose, which is an energy source, and oxygen, which we breathe. Okay. In this case, this is the reactants. This is the product. Okay. Now, pretty much all chemical reactions are reversible with a little asterisk here under the right conditions. Okay. Products of the forward reaction become the reactants for the reverse reaction. So here we have the hydrogen and oxygen forming water. Under the right conditions, you can actually take water and break it up and form hydrogen and oxygen. So here we have reactants, products, reactants, products. Okay? These things can form a chemical equilibrium if the forward and reverse actions are the same. And at this chemical equilibrium, all things stay in the same relative concentrations. We'll go into this deeper when we talk about metabolism. All right, so 2.4, chemical reactions make and break chemical bonds.